No, it was just sort of a one-time thing. All right, good morning and welcome. Let's begin with some announcements. All right, your first more detailed homework assignment, your first quantitative homework assignment, due on Tuesday at the beginning of class. And so please use engineering paper for that. And the homework set is there on screen. It's also in the course schedule document that I handed out to you previously. You know, that's also posted on MU Online if you happen to lose the paper. Those are the problems you need to work. We're going to go over one of those problems at the end of class today. I'll just sort of give you a couple of hints because it's a little bit tricky. But the rest of them, through just the exposure to the concepts that we did last time and some examples that we'll work today, I think you should be able to work through without any trouble. You know, just as a reminder, I have office hours 5 days a week. And if you'd like to come see me outside of my office hours, if I'm there, I'm happy to help you, or we can set up an appointment if you send me an email in advance. So I'm anxious to help you this semester. Please let me know anytime you've got questions. I've been working through homework 1, reading your responses, and I've got all but 2 of those graded. So in some cases I left comments for you, and I think that you can get at those comments by going through the grade book that's online. All right, so any questions on these announcements before we dive in? All right, let me dim the lights, but this really isn't the best projector. It's kind of hard for you to see, but hopefully you can get a sense for what's going on in this picture. What are we looking at? Syrup? Maybe it's oil? Is it water? I don't know. I think your classmates are skeptical. Why would you say, who says that this isn't water? I think it's honey, personally, but I don't know. I didn't taste it. Maybe it's a thick motor oil. But how do we know that it's probably not water? What are some of the key indicators for those of you who think that this is honey or something besides water? What are the clues? What is it? Okay, viscosity, I heard the word viscosity said, but what are the indicators that this fluid is more viscous than water? Okay, yeah, the air is entrained. If this was water, then the bubbles would just rise to the surface more easily than they appear to be kind of stuck in the fluid here. Another thing, I would assume this is being poured out of a spoon, and there's just something about the photo that makes me think it's pouring slowly. I guess it's because it's all sticking together. You know, water, if you pour it, it begins to sort of go into smaller droplets and it accelerates away from itself. But here, the fluid is sticking together, and so you can see this tapered appearance kind of is what's giving me the visual clue that this is, some might call it like a thick substance, but you know, calling it a thick liquid isn't the technical term for it. What we're seeing here is a manifestation of viscosity. So let's watch a brief video clip that is another illustration of differences in viscosity between 2 fluids that appear to be identical. When we first look at them in the beakers that they're going to be in, they're essentially the same looking fluid. Let's see if this will open up our browser. This is a very slow computer. Time is money, and we're wasting money. Almost there. What'd be the worst is if we get an ad now. Hopefully it's our lucky day and we won't. All right. So you shake it on the left, it's just slurping around like water. Something's different. He was shaking it, and it wasn't going back and forth like normal. So they're both clear liquids, and in fact these 2 liquids have a very similar density. It's not that one is heavier than the other. They both have about the same weight for the volume in question. But one of them is pouring slowly, and you can see that thick cascading appearance. It's because the fluid on the right is glycerin, and it has a high viscosity. It's viscous. And so what what was the force that was being applied at the beginning here? Just shaking it back and forth. That was a shear stress that was being applied. So strain is the deformation of a physical body under the action of applied forces. In the case of a solid, if we apply a force, I've got a metal ruler here, a flexible metal ruler. So if I push on the ends of it, the way that it manifests the fact that I'm applying a shear stress is it bends. And this is made out of stainless steel. And so it has a certain proportionality between how hard I push and how much it deflects. What would you expect if this was made out of titanium? How would things be different? It would be harder for me. It wouldn't be as flexible because it would have a different shear modulus. The amount of force that I apply would cause less of a deflection. In the case of a solid, that relationship between the stress that's applied and the shear strain that results is the shear modulus. Well, in the case of a liquid, there's the same proportionality there, a relationship between how hard you push on it and how much it deforms. And that relationship between the two factors is viscosity. So it's kind of an analogy. In solid mechanics, we have shear modulus. In fluid mechanics, we have viscosity as our proportionality factor. Now, another way that we can consider solids and liquids as being different, it says here that a solid ceases to deform when equilibrium is reached. What that means is I'm pushing with a certain force on this ruler. And if I don't increase the amount of force, it's only going to bend so much. But in the case of a liquid, I can keep applying the same amount of stress to it, but it continually deforms because it's fluid. It will just, if I put an egg beater into a container full of a liquid and I turn on the egg beater, as long as I'm applying that shear stress, it's going to continue to deform. So that's one of the distinguishing factors between solids and liquids. All right, here's a picture of a beautiful river. I don't know where this photo was taken, but let's say maybe like Wyoming or something, right? It seems like a Wyoming kind of a picture. From a photo like this, somebody would say, is the water moving quick or slow? And it doesn't look like there's a lot of rapids. Here are some ripples on the left side of the image. That may be where some rocks are protruding out of the water. But when we talk about the velocity of a river, it turns out that actually there isn't one velocity for a river. There's lots of different velocities, not only up and down the length of the river, but also side to side. There are different velocities, and up and down in the velocity. So if we think in 3 dimensions, 1, 2, and then 3 vertically, how would you expect the velocity at the left bank of the river to be different than the velocity in the center of the river? Which is going to have the higher velocity? The center. Well, why? You're right, but why? Friction. Yeah, so you're thinking that there's some sort of resistance that's being applied at the left bank and the right bank as well. Now, what about vertically? Is it going to be faster at the top or at the bottom? It's going to be faster at the top. How come?
Because it's rubbing against air instead of rubbing against soil.
Very good. Yeah, it's not rubbing against nothing. It's touching the air. And so there is some resistance, but not nearly as much as at the bottom of the stream where the water is in contact with a solid. So that's what we're looking at here, is a cross-section of the water is flowing from left to right. This is what's called a velocity profile, or a velocity distribution. And what it's showing is that when the water is touching the soil at the bottom, it has 0 velocity. The water's going the same speed as the solid that it's touching. But then the further away you get from that surface that's applying resistance, this frictional surface, the further away you get from the friction, the faster the velocity is. And so here we have dv, which is increase in velocity. So that is this horizontal component. The further away from this axis we get indicates a higher velocity. And then dy is how far vertically we're getting from the bottom of the stream. And you can see that the velocity is increasing fast at first, but then it begins to taper off a little bit. It's a non-linear velocity profile. And that's because, as you get further away from that solid surface, it speeds up quickly, but then it's like diminishing returns. Getting a little bit further away from this surface that's so far down, it's exerting less of an influence the further we get from the bottom of the stream. So this is an example of fluid viscosity. And if it's water that's flowing through a stream, we'd have one profile. But different substances would give us a different velocity profile because of the viscosity. If it was pancake syrup that's flowing down a river, it would be moving slower. And so the velocity profile would be shifted to the left, because for a certain shear stress that we're applying, which is the slope of the river, it would have less of a deformation. It would be a lower velocity. But if it's a fluid that's less viscous than water, like alcohol, then the river would be moving more quickly. So think of that, a river full of alcohol and pancake syrup. Which would you choose, Who knows? All right, so let's watch a video clip before we go into some of these definitions. Another one. All right, so the water in this picture is moving from right to left. This is like a straw, hollow straw, that's going to be injecting a dye. So what we'll see when they begin injecting the dyes, you'll see the dye moving towards the left, and that's an indicator of the flow direction. But it's not a sticky dye, it's just a water-soluble dye. There's nothing magical about it, but you're going to notice that the dye that's injected down low in contact with the surface is going to behave differently than the dye that's injected in the middle of the stream, further away from the surface. Okay, so the dye is continuing to come out. You'll notice it's flowing away, but this dye is still stuck there at the bottom because of the no-slip condition. Because until the person puts the spoon there and sort of really agitates it, just the general motion towards the left isn't providing enough velocity at the bottom to move that dye out of place. So let's do some definitions here. We're going to think of viscosity as resistance to flow. You can think of that as kind of a non-technical definition. We're going to have other definitions. We're going to have a graphical definition. We're going to have fluid properties we can look up in the text, but viscosity is resistance to flow. So we'll use V, the letter V is velocity, and remember last time we used V with a cross through it to indicate volume, a strike through it. Y is the distance from the bottom, and then rate of strain is dV dy. That is how much force the fluid is encountering. You can think of it that way. So the proportionality factor, dynamic viscosity, is the relationship between how much a fluid deforms when we are applying a certain amount of stress to it. So shear stress is going to have units of force per unit area. So newtons per meter squared, for example. That is a way for us to measure how much we are pushing on the water. And here is our first relationship that we're going to use to talk about viscosity and its effects. This is showing how we can relate the rate of deformation and the shear stress. And so remember earlier on the previous slide I said it's a proportionality factor between how much it's deforming and the shear stress that's applied. And so here's that relationship. Is dV dy is its reaction, and tau is the shear stress or the force per unit area that's being applied. So a fluid with a high viscosity is going to have less velocity for the same shear stress that's applied compared to if a fluid has a low viscosity, then it's going to have more velocity on a relative basis. So think of it this way. This room is full of air, and so it's easy to walk around when you're in air. So it's easier to walk through air or water. Think about walking through a swimming pool. It's a little bit awkward. You can't move as quickly. So why? why can't you move as quickly through water as you're able to walk through air? Okay? That's what causes viscosity, is the intermolecular forces. So like, the water is resisting your motion. Yeah, it's trying to get out of your way, but it gets out of your way more slowly and with more difficulty. You know, you have to apply more of a force to push the water around your legs. You don't have to apply much of a force to walk through air. You know, race cars have to worry about wind resistance. I guess regular cars do as well. But when we're walking, we don't usually notice the air resistance. So the why behind that is because there's less friction in air, and the rate of deformation, the air deforms more easily and more quickly when you apply the same shear stress. So that motion of walking, you can apply the same force, but you'll just go more slowly because the water is moving out of your way at a lower speed because of its viscosity. Now we can represent that graphically. So here is how we can define viscosity in a graphical way. Let's look at the horizontal axis here. Rate of deformation is just that idea of how quickly something's moving out of your way when you apply a force to it. And that force is the shear stress that we're talking about in the vertical axis. So in the case of air, what this means is I only have to apply a tiny little shear stress to get a lot of deformation. And that's what I notice when I'm walking through the air. I'm not applying any effort, and the air is getting out of my way very easily. But in the case of water, for that same amount of shear stress that I'm applied, it's deforming. Its rate of deformation is much lower. So here it's saying du dy. Du is the velocity relative to dy, which is the distance. In the previous slide, I think we had v as velocity. Sometimes u is also used as a variable for velocity as well. So the difference between water and air is that for the same amount of shear stress applied, water doesn't deform as quickly as air. And oil deforms even more slowly. And so oil has more viscosity, which means a pool full of oil would be even more challenging to walk through. You'll notice here that we've got these variables A and B where it's talking about the slope of the line. So B is the horizontal component of the slope, A is the vertical component of the slope, and what this expression is showing is that you can find the viscosity graphically by having the shear stress as the vertical component of the graph and the rate of deformation here in the denominator, and that is viscosity. It's the same thing as this relationship, but it's showing you that A and B are the graphical slope of the line. If you have a graph of shear stress and rate of deformation, then experimentally you can determine the viscosity this way. And that's what they do, is they're actually lab instruments where you can characterize the viscosity of an oil by putting it between two plates and then pulling the plate and seeing how hard you have to pull on the plate, and then that will give you the viscosity of the oil. Any questions so far? Because this is new stuff. You know, some of the material from last time you probably had before, but I doubt in previous classes you've thought so much about viscosity. So I'm happy to entertain any questions.
How are these plates suspended?
Good question. So you're talking about in the instruments. Usually they'd be floating in oil, and so maybe like the weight of it is suspended with a cable, and it's just the sideways resistance that they're trying to measure. Yeah, we have an example in just a moment where we'll be calculating the forces of a plate that is suspended in oil. So viscosity is the slope of the line, and it's the ratio between shear stress and the rate of deformation. There's a lot of different words associated with viscosity. Sometimes we just call it viscosity. There's also absolute viscosity. There is kinematic viscosity. And so let me tell you what kinematic viscosity is. A lot of the equations that you'll be working this semester and beyond have both the viscosity and the fluid density in the equation. And so kinematic viscosity is an effort to kind of normalize fluids' viscosity relative to their density. In other words, combining both of these two things together in a single parameter. So kinematic viscosity is the ratio of absolute viscosity to fluid density. In other words, if you have the absolute viscosity and divide it by the density of your fluid, then that would give you the kinematic viscosity. So for instance, water has a typical viscosity of 1 times 10 to the minus third Newton seconds per meter squared. That's the typical absolute viscosity of water. What's the typical density of water? 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter. Okay, so if we divide these two together and try and find our kinematic viscosity, then we end up with 1 times 10 to the minus sixth meters squared per second. And that's our typical, like, room temperature viscosity of water. As you might expect, fluids have their viscosity change dramatically as a function of temperature. Anybody here ever changed the oil in a car before? If you want to get it done quick, is it better to change the oil when it's cold or when it's hot? Hot. Why is that? It runs out of the pan a lot more quickly. Yeah. So increases in temperature increase the viscosity of gases, but decrease the viscosity of liquids. We'll see a graph of that in just a moment. So here's some terminology. If I just say viscosity without any modifier like absolute or dynamic, what I mean is mu. Absolute viscosity means the same thing. Dynamic viscosity means the same thing. So all three of these are referring to the same kind of viscosity with the same units. Kinematic viscosity is what we've just shown here, where you're taking the viscosity and dividing it by the density. All right. So if we go from shear stress to force, the way we do that is if you have a shear stress, which is newtons per meter squared, and multiply it by area, then you'll end up with force, units of newtons. So here's how we do that in the case of viscosity. du dy. Anybody remember what this grouping is called? Du dy? It's the rate of strain. So if we multiply the rate of strain by the area that is in contact with the fluid, and we multiply that by the viscosity, then we will know the force required to cause that rate of strain, where the rate of strain is like a velocity. So when we're pulling on a plate, how much force is required to achieve a certain velocity is calculated with this expression. Here are the units. You know, this semester I'm going to be really emphasizing units a lot. And it's such a great habit for you to get in to include your units in every calculation that you do. Don't just write the numbers and plug the numbers into formulas. Write the numbers and the units that go with them. And the reason why I suggest that is it's always going to help you avoid mistakes. If you put centimeters instead of meters, it's not obvious unless you write the units right next to the number that you're talking about. Because if you just put the numbers in, it's not going to raise the same red flags as when you go to cancel out the units at the end of the problem. So I'd really encourage you, and all of the examples I show you on the screen or on the board, I'm always going to write the units along with the number, because I think it's a great habit for engineers to be in. Okay, now du dy can be simplified if we assume a linear velocity distribution, just velocity divided by distance. And you can make an assumption of a linear profile for the problems that we're going to be solving in the homework. So here is that tank I was talking about. Let's assume this is a side view of a tank full of glycerin. Glycerin was that liquid on the right that when you shake it back and forth, it's kind of viscous. Here is a rectangular metal plate. We can only see how long it is. I think in the problem statement it defines its other dimensions. It's 3 by 2. It ends up not mattering if it's 3 long or 3 wide, but we know the dimensions of this is 2 by 3. Now it's in a tank, and the distance to the top of the tank is 1.2 meters, and the distance from the plate to the bottom of the tank is 2.4 meters. And we want to know for this glycerin, which has a viscosity of 0.15 newton seconds per meter squared, how much force is required to achieve a velocity of 0.58 meters per second. So clearly we're just going to be substituting into the formula here, but there are a couple of things we need to keep in mind. And one is that the force that this plate is encountering is actually coming from two places. The force is partly due to the interaction with the fluid above the plate, and it's also due to the interaction with the fluid below the plate. And so we need to find the force acting on the top and the force acting on the bottom. So this will be a two-step process where you substitute both of these two distances into the formula separately and then combine the forces together. All right, so I'm going to pause the recording. I'd like you to attempt this calculation, try and find out what force is required, and I'm going to be circulating around the classroom with a solution, and then we'll take a look at it on screen as well. So if we go back to the drawing, we have to consider the distance to the top separately from the distance to the bottom, because both of them are applying a force to the plate, and then the combined force is what has to be overcome through this external force in order to achieve some rightward velocity. So in the calculations here, you can see I've identified the distance to the top, distance to the bottom, velocity, viscosity, and then done the substitutions. Fluid viscosity, plate area, velocity, and then the gap distance between the two surfaces that are moving in reference to each other. So the top force is higher because it's closer to the top. So that top is exerting more of a resistance than the bottom of the tank because the bottom of the tank is further away. So I think that's consistent with what we were saying earlier about the river. The closer you are to the bank, the more resistance that you're encountering. And that's why the velocity is lower at the edge of a riverbank than at the center, is because of the force requirements. And so here it's the same effect, essentially. I got a good question as I was circulating around. On this slide, I didn't really talk about all of what this expression was. That is, I'm substituting in the units of here. So viscosity has units of newtons meter per second squared. Area has units of meters squared. du has units of velocity, so meters per second. And then dy has units of meters. And if we cancel all of those out, all that's left is newtons, which is what we hope to see when we're measuring force. And so the units cancel for the formula. If you ever have a formula and the units don't cancel, double check the formula. There may be a mistake. So any questions about this example? Yes?
Is there like a set of how far you want to compare decimal places out to?
Good question. Very good question. So when you're doing your calculations in your calculator, in all of the intermediate steps, leave that precision in the calculator. So in other words, don't round off in every step, because if you round off in every step, it'll magnify the error. So in my solution, in this case, I guess we did things, the entire thing in like one step. But let's say you did 0.58 divided by 1.2. If you round it off and then multiplied it by these things, then that's introducing an error. So what I'm saying is keep everything going in the calculator, and then in the end, round off usually one more beyond what you see. So like when this says 6 square meters, even though the decimals weren't in the problem statement, it's probably the plate is exactly 3/2. And so that's probably a precise measurement. But we only know the viscosity to 2 digits of precision. And so 2 or 3 decimals is, I think, a reasonable way to express. So here I've overdone it. When I say 0.6525, I probably should have just said 0.653. But, as far as like in an exam, I wouldn't penalize you for having too much precision unless it's just like ridiculous, page after page. But also don't round off too much. If you said 0.7, then that doesn't give me enough information to know, like, is that because of a round off or a calculation error? So, I think you get the feeling just somewhere in the middle based on the input numbers that you've got going into the formula. Thank you for that. Any other questions? All right. Some other things about viscosity. It doesn't matter the pressure that's applied to a fluid. The viscosity of the fluid is independent of the pressure. So at the bottom of the ocean, the viscosity of seawater is the same at the top of the ocean, assuming that the temperature is the same. And that may or may not be the case. But assuming constant temperature and constant salt content, the viscosity is not affected by pressure. Now, what causes it? It's because of molecular forces, and I think somebody mentioned that earlier. It's kind of the attraction of the molecules to itself. And in the case of a liquid, when you increase the temperature, then those cohesive forces are getting weaker. And that's why viscosity decreases with increasing temperature, is because the bonds are less attracted to each other with a heated fluid than they are with a cool fluid. But it's kind of an interesting contrast in the sense that for gases, when you increase temperature, the molecules are moving around a lot faster. And because of the collisions and the increased shear stress, then that increases the viscosity of gases. And so we'll see an illustration of that in, well, let's just jump to it right now. Here's an illustration in the case of kinematic viscosity. Increasing temperature decreases viscosity for a liquid like crude oil. But in the case of a gas like air, the viscosity is increasing slightly because of the increased molecular motion, more collisions, and it's just the fluid particles getting in the way of each other, and so the gas becomes more viscous. Not a lot more viscous. This is a logarithmic scale over on the left side, but it is becoming more viscous, whereas the liquid is becoming a lot less viscous. So there are some interesting temperature differences. Okay, here is Sutherland's equation, and it's useful when you need to estimate viscosity of a fluid. So a situation when you may need to estimate the viscosity of a fluid would include a homework problem. So you're going to be using Sutherland's equation, and what you can do is use the viscosity at a known temperature. That's what this is. Viscosity at a known temperature T0, where it's given in terms of absolute temperature, so Kelvin. And then you use Sutherland's constant. For air, it's 111 Kelvin. For other gases, you've got that in the table. Then you can find out, for example, here, we're going to calculate the viscosity of air at 95 using the viscosity of air at 50 as our baseline. So do that. Convert the temperature into Kelvin as your first step, and then use Sutherland's equation to estimate what will be the viscosity of air at 95. When I was a student, I got in the habit of triple checking every calculation I did. And to make that slightly less tedious, I decided that I would write out as many steps as possible and create like groupings. And so you'll notice here where I've got the temperature relative to the original temperature, then below that I've got 1.139, That's so that when I go through a second and third time, I can make sure that it matches up. And so, paper is cheap, pencil lead is cheap. Don't try and make it so small and compact that you forget what you were even using as your method. One of the interesting things about engineering is, when you graduate and working professionally, you'll do a design, and at the time you do the design, it'll make perfect sense to yourself. But then you'll come back later and you'll look at the design and you'll wonder, what was I thinking? Like, not necessarily that there's a mistake, you just won't remember what you did or why. So I learned very early on the value of detailed calculations, because later on down the line, you're going to either have to teach a client or teach yourself what happened and why. So that's my little mini lecture for now on that. Take up plenty of space for examples and homework. It'll pay off. So here we convert the temperature into Kelvin. We've got the Sutherland constant. Just do the substitutions. And when you do, I hope you got 2.15 times 10 to the minus fifth Newton seconds per meter squared. So that's the estimated based on what the temperature was at another temperature. What the viscosity was at another temperature. If you actually go to the book and look up the actual value is exactly the same, 2.15. That's from table A3 in the book. Now, it doesn't always match up perfectly like that. Sutherland's equation is just like an empirical relationship that's been observed to work, where you're fitting observed data to an equation that you've created to try and create a best fit line, but it works pretty accurately within this range that we're working for the example. Are there questions on this one? Anything you'd like to check on before we move on to the next topic? All right. So we've already seen this slide, the relationship between temperature and viscosity. This is a fun one. Newtonian versus non-Newtonian fluids. Water is the liquid that we are very well acquainted with. And in the case of water and many other fluids, they're considered Newtonian, which means that the shear stress is proportional to the shear strain. A shear thinning fluid is one where the ratio of shear stress to shear strain decreases as the shear strain increases. That's hard just from what's written there to envision, but in the case of toothpaste, ketchup, paint, and other shear thinning fluids, what that means is that the more you work with it, the less viscous it gets. So if you apply a really hard force to it, that force changes the viscosity. So the fluid is sensitive to the shear stress that is being applied. And ketchup is an example of that. If you have a bottle of ketchup and you shake the bottle to get the ketchup out, part of the reason you're doing that is because it's a tiny little hole and so you're shaking it so much. But as you shake that bottle of ketchup, you're actually making it less viscous, and so that it can flow more easily. You're changing the viscosity of the fluid as you shake the bottle. In the case of a shear thickening fluid, that's a fluid where the viscosity is increasing in response to the shear stress that's applied. Let's take a look at one of those kinds of fluids. We've got a video clip of that. It actually becomes more viscous as you interact with it. And these guys are having a ball. That is a swimming pool.
It's all over. It's all over. He's going down. It's not going to work. Oh! It's eating you.
You gotta get out slowly. If you try and jerk your foot out, you might be able to get out. But if you slowly take your foot,
Slow and steady.
you'll be in there all day. All right. You get the idea. So it's an interesting fluid. Let me see this one. All right. Here's another one of non-Newtonian fluid.
What's this? Your new birth certificate. I had your name legally changed.
Dolores sucks at fantasy. Does Mom know about this?
Yeah.
All right, ready? Yeah, ready? Go for it.
This is the same thing. This is cornstarch that just added a little food coloring to it. Oops. So the subwoofer is vibrating, and then the viscosity of the fluid gets more solid
once you set it off, it's like,
as it's vibrating.
oh,
so now
there you
they've
go.
got like a
And it just
high-speed
collapses
camera
back into liquid
focused in
afterwards.
on
Yeah.
it. Just a second here. There it is. So the subwoofer is changing the frequency that it vibrates. You know, the low notes, it's a slow vibration. The high notes is a fast vibration. And the change in sound has a changing effect on the fluid itself. This almost looks animated, doesn't it? But it's not. You can't really see it. Oh, what a crappy projector. It looks great from my end. All right. Watch the video and you'll be able to see it. Here's a diagram that shows Newtonian fluid, shear thickening, so the viscosity is getting higher with the shear stress that's applied, and then shear thinning. The trend with shear thinning is as you apply a force to it, it becomes less viscous. And so the slope of these lines is the relationship that is linear in the case of Newtonian and nonlinear for shear thinning and shear thickening. We'll play around with some cornstarch and water in lab. All right. I don't have a subwoofer that we can play with, but if any of you want to bring one in, that would be really cool. So, all right. A couple of the problems in your homework has to do with looking up values related to fluid properties. And so I wanted to review with you what's available. For example, if you wanted to find the viscosity of water at 80 degrees Celsius, there are some tables for specific temperatures, and so you can go to the table and find, here's the dynamic viscosity, 80 degrees Celsius, there's the value. How does the kinematic viscosity of oil change from 50 to 100? Well, this one is just for water, so you wouldn't be able to do that for the oil. Also here, they do have some oils, but this is just for certain temperatures. This is for 4 degrees Celsius. And, oh wait, no, this is 38 Celsius for the oil. And so what you need to do in some cases is rather than going to a table, you'll have to go to a figure. And so if we wanted to know how the kinematic viscosity of oil changes as a function of temperature, then you'd go 50 Fahrenheit, you go up, find the oil in question, SAE 20, which is this line. So here's the SAE 20 line. It crosses over. But you'd get it at 50, and the irony is that the line doesn't even go to 50. So you'd have to extrapolate. You'd have to continue that and find where it would intercept and find the difference in viscosity. Here on the left-hand axis, vertical axis, is kinematic viscosity in feet squared per second, and on the right axis is meters squared per second. So you either use temperature from the top in Celsius or Fahrenheit from the bottom, find the intercept, and then go left or go right. The point is that all of these tables are in the back of your book. Appendix A has a lot of different fluid properties. Okay, the last thing we're going to do today is the ideal gas law. And you probably remember from chemistry, PV equals nRT. So what if we rearrange that? P equals nRT divided by V, where V here is the volume. There's no cross through it this time, but. And R is the universal gas law constant. That is just in general for gases. Well, what if we multiply by the molecular weight of the gas? We can do this if we have it in the numerator and the denominator. It's just like multiplying by 1, so it doesn't change anything. What it will allow us to do is create a new variable grouping. Here, if we have the number of moles multiplied by the molecular weight of the gas divided by the volume, that is the density of a gas. That's the definition of density. So making that new grouping allows us to say this. You can get the gas law constant for a specific gas instead of using the universal gas law constant, which is just in general gases. But if you look up the gas law constant for helium or for hydrogen or oxygen, whatever gas you're working with, you can find a specific R for that gas. And then this ideal gas law turns into that you can find the pressure of a gas by knowing the density, the R, which is the gas law, the gas constant for that gas, and the temperature. And the temperature that we'd use would be in Kelvin. So this ideal gas law will allow us to solve problems like this. Let's take, for example, what if we had a room that's approximately 4 by 5 by 8? And, that's roughly the dimensions of this room. If we had the pressure as 100 kPa, which is approximately atmospheric pressure. Atmospheric pressure at sea level at standard temperature is 101.325 kPa. So here it's 25 Celsius, 100 kPa, and it's 4 by 5 by 6 meters, the volume. And we can look up the R value for air. And here, the R value that's shown there has units of joules per kilogram Kelvin. We have to be even more attentive of units when we work with the gas law because there's so many different R values you can find. Like you can look up, all of these are R values for air, but with different unit systems. And so let me show you something on the board here before I turn you loose to do the calculations, because ultimately I want you to find the density, the specific gravity, and the mass of air in the room. Before you start substituting, let me show you a little bit about why we picked these units. Out of this list of all the units we could have chosen for the R value of air, this is the universal gas law, why did we choose joules per kilogram Kelvin? The reason for that is we can take, bring the lights up. If we have an R value of 287 joules per kilogram Kelvin, well, that's the same thing as 287 Newton meters per kilogram Kelvin, because a joule is the same as a Newton meter. And what is a Newton? Anybody remember? Good, that's right. So that's the same as 287 kilogram meter per second squared multiplied by meters kilogram Kelvin. Okay, what we're doing is we're expanding everything out to its baseline units. And so now we can, from that, cancel out, and what we have is 287 meters squared per second squared Kelvin. This is the R value we're going to need to put into this equation and get everything to cancel out. Because we're going to put it in here. We're going to multiply by a temperature in Kelvin, so that will cancel out the kelvins in the denominator there. We're going to use pressure. Now pressure has units of, pressure is measured in pascals, which is the same as newtons per meter squared, which, remember, a Newton, kilogram meter per second squared divided by meter squared. So that's going to be kilogram second squared meter squared. So when we get pressure, hopefully everything's going to cancel out so that we have these units. So with that, I'd like you to try and figure out 3 things about this room for the temperature and the pressure that we've got. Find out the density of the gas, being air, the specific gravity, and remember SG from our last class, we said that specific gravity is the density of something relative to the density of water. And you remember the typical density of water to use for that. And then the mass of the air in the room. All right. So I don't expect you to go through all of the units backflips every single time to show like why this has units of kilograms per cubic meter. But just the first time I wanted to prove to you that if you put pressure, which is pascals, and R value, which is units in this case of joules per kilogram Kelvin, and temperature in Kelvin, I wanted to show you how we get a density unit out of that, kilograms per cubic meter. It does work out. This is showing the steps. As I was walking around, it seemed like most people got 1.17 kilograms per cubic meter, so that's good. That's the density of the gas. And once we have the density, it's easy for us to find the specific gravity. Remember, the definition is just the ratio of whatever we're talking about, in this case air, relative to water. So water has a density of 1,000 kilograms per cubic meter. This has a density of 1.169. So there's our specific gravity. Yeah?
For that to be in scientific notation.
I don't really have a preference. Yeah, it's fine if you do it in scientific. I mean, if there was a few more zeros on here, then I'd start to have a preference. But for that, I don't really. That's a good question. For the mass, the way we do that is just multiply the density by the volume of the room. Sometimes if you don't know the formula for something, you can derive the formula yourself just by considering the units. You know, what's in the problem statement? You know the volume of the room, so from that you are going to have cubic meters of gas. Well, when you found the density, you had kilograms per cubic meter. So those units gives you the clue that you should multiply the two together, and you're going to end up with kilograms. That's what I was asking, is the mass of air in the room. Mass is measured with kilograms, so sometimes the units are helpful not only for finding your mistakes, but knowing what operation to do in the calculator. So that one, 140.3 kilograms of air. So in this room, or a room approximately this size, there's 140 kilograms of air. When I was younger, I had to carry my bike home for whatever reason, like the chain came off, and I let all the air out of the tires because I thought it would weigh less if I did that. Maybe it was a little bit less, but it was still pretty heavy. So I was trying to outsmart gravity. Never win when you're trying to outsmart gravity. All right. Here's one of the homework problems. Did you have a question? Only on the videos. Yeah, I don't post the PDFs of them anyplace. It's just if you want to look at them again, you can get at them through the videos. Yeah. Okay, so here are some key ideas, and I hope showing you these key ideas for this problem will make it a little bit faster for you to solve it than if you just were starting on it from square one. What it is a cylinder that's falling down through a shaft, a hollow shaft. And what we know about it is that this shaft has a film of oil around the edge. And so it's a little bit like a piston in a cylinder, how the gap between a piston and a cylinder is lubricated with oil. Same thing here. We have an oil film that's lubricating the descent of this cylinder as it falls downward through a different cylinder, a pipe. The problem statement says, derive a formula for steady rate of descent. Okay, what I really want you to find is what's the velocity when this is in equilibrium? Meaning once it's reached its terminal velocity, when there's equilibrium between the weight, because the weight is acting down. What do we know about this cylinder? It has a weight of 15 newtons. So you can do a force diagram. The weight of the cylinder is downward, and the cylinder itself is moving downward. So when it says rate of descent, that means the cylinder is moving downward. Descent gives you that clue. So if the cylinder is moving down, the shear force is up on the cylinder. The oil is trying to resist the movement of that falling cylinder. So the oil is pushing up on that outside surface of the cylinder. Now sometimes on this problem, students get used to calculating area by pi r squared. That's a formula for area, right? Or pi d squared divided by 4. That's also a formula for area. But here, when we use the equation to tell us the shear force, there is an area component of that, but the area that it's talking about is the area that's in contact with oil. And here, the area that's in contact with the oil is the outside of the cylinder. It's not the top or the bottom of the cylinder that's touching that thin film of oil. It is the outside area of the cylinder. So I wanted to give you that hint. So here what you're going to have to do is find the velocity. In this formula, which component is velocity? du. Yeah, du divided by dy is the rate of strain. What's dy? How did we use that in the previous example? It's the distance. You say the gap. Yeah, so you're going to have to be mindful of what is the distance between the cylinder and the pipe that it's in. We are given the dimensions. We're given that the pipe has a diameter of 100.5 millimeters and the cylinder has a diameter of 100 millimeters. So what's the gap diameter? Or what's the gap distance? Someone said 0.25. Why'd you say that? Yeah, because it's on both sides. Good. The gap is all the way around it. And so you've got a total of a half millimeter of distance between them, but we assume it's falling through the center line of that pipe and that the space is evenly distributed all the way around the cylinder. Okay, so the key things I wanted to talk to you about are the area that matters here is the outside area of the cylinder because that's where the oil is touching. The gap distance, you have to be careful there because sometimes it's easy to say, well, the gap distance is 0.5, but really it's half that because the gap distance is on both sides of it. And those are the hints I wanted to give you. Let's take one final look at these announcements so we can all keep on track with what we need to do. Your homework assignment is due on Tuesday. The early bird gets the worm. If you get started on this today, then think of how many opportunities you've got to ask questions. You can send me an email tonight. You can come see me tomorrow. Come see me on Monday. But the person who starts Monday night at 11:35 p.m., I'm not going to be answering their emails, right? So get an early start and you'll thank yourself later. Have a good one.